Worked problems for Chapter 20, Electrochemistry. Most of these problems were taken from Zumdahl's chemistry book. There may be a few from Brown and LeMay, and then there were a number of multiple choice questions that were taken from Mr. Mack's AP chemistry site. Answers are provided by the author. Next slide. So here are the references. Very occasionally, one of these sets will have a problem from McMurray, but most of them are from Zumdahl. Next slide. Next slide. Okay, so these problems are not super difficult, but you just have to be sure you understand what's going on in the problem, so we'll try to explain that. So for this first one, sketch this cell. This is kind of like the zinc copper cell, except that it's got magnesium instead of zinc, but otherwise it's basically the same thing. Of course, the voltage will be a little bit different. So we want to sketch it, show the direction of electron flow, and so forth. So we want to look at this. We'll have to go to the next slide to see the values for the voltages for the half cells. Notice we're assuming that all the concentrations are 1 molar, which means that they're going to be standard values. So we already have done this before for copper. Magnesium we haven't done, and then find the cell value for the E naught value for the cell. So we can't really do this stuff unless we look over, but we'll get to that in just a second. But before we even go, I can tell you that magnesium will reduce the copper, which means that the way it's written here under B, right here, that's the way that it's going to go. That's actually put in there to make it easier for you to see what's happening. So we're going to start off with magnesium metal on the left, and that'll go to Mg2+ on the right, and copper 2+ on the left. We'll go to copper metal on the right-hand side. Let's go on to the next slide and figure out the voltage. So we've got the two things in red here that are in this problem. You can see here by looking at this, remember this is a standard reduction potential, and we can tell that because we can see if we look over here that the things are gaining electrons on the left-hand side of the arrow. So the ones that are on the top are going to stay the way they're written, and the things on the bottom will have to be reversed because they are going to reduce the things on the top. So for this one, the thing down here at the bottom, which is the magnesium, will have to be moved over. This magnesium right here will have to be moved over to this side over here on the left. So in other words, we just have to reverse this direction of this reaction. So remember the rule, the thing on the bottom reduces the thing on the top. And when you reverse the direction of this one, which you would have to do, then you have to change the minus sign here to a plus. So this becomes plus 2.37 volts for the magnesium half reaction. And then the one up here at the top will stay the same. So it will stay as plus 0.34 volts. So we'll add those and we'll get plus 2.37, excuse me, plus 0.34. So that's going to be approximately 2.7 volts. Then to sketch this, we'll put the thing that's being oxidized on the left. In other words, the thing that's giving up electrons. Well, that's going to be the magnesium because the magnesium is losing electrons. Remember that we have to reverse the direction of this one. So this magnesium metal here is going to wind up over here on this side, which means it's the one that's going to be oxidized. That occurs at the anode, and we always try to put that on the left. One of the problems we'll do in just a minute, one part of that problem, we can't really do that, and I'll explain it when we get to it. But basically the rule is put the oxidation on the left and the reduction on the right, the anode on the left and the cathode on the right. So that means the magnesium electrode goes in the beaker or whatever that's on the left-hand side, and the copper electrode will go on the right. We'll see a picture of it in just a moment. The magnesium would need to be immersed in Mg2+ ions, which would be a solution, a water solution. And then the same thing for the copper, that would be in copper 2+. You'd have to have a wire with a voltmeter, and you'd have to have a salt bridge just to complete the circuit, right? And then the electron flow would be going from left to right, which we try to always make it that way. Let's go to the next slide. So here, the magnesium half cell would be minus 2.37 volts, but we have to reverse that. So that would become plus here. So this would become plus. And then when we add that to 0.34, we get about 2.7 volts. We already said that. So let's go to the next slide. And here we have a picture of what we would have if we drew this cell. So on the left-hand side, we've got magnesium, and it's immersed in magnesium 2+. And on the right, we have copper, and it's immersed in copper 2+. And we have the connecting elements. We have the salt bridge here, and we have the wire here. The electrons are going from left to right. Again, we always try to get it that way. And here's our voltmeter, and that's going to read about 2.7 volts. 2.7. Okay, anyway. And I think that's about it. Okay, so that's all you would have to do. So figure out which way these things are going to run by looking to see which one is on bottom and which one is on top in the chart. Okay, so let's go to the next slide. So give the standard line notation for each cell in 25 and 29. We only did the magnesium copper. So to do this, what we would want to do, and I'll just go ahead and try to write it, but it's really hard to do it, but magnesium would be the thing that's being oxidized, so we start with that, or we could also say we start with the anode. And we're starting with magnesium metal, so we write magnesium, draw a line, and then write what it goes to as a product. So don't let this confuse you. Even though it's on the left-hand side of the salt bridge, this is really difficult. And I don't want to spend a lot of time on it, but I'll try to do the best I can with it. So 2+ here. Okay, and then that's the anode. So this is the anode. Draw a double line to show where your salt bridge is. And then in the cathode, we had copper 2+, Cu 2+. And notice that this is not the same thing we had on the left-hand side over there for the magnesium. And then another line, and then just copper. I know this looks horrible, but anyway, it is what it is. And that copper is not 3+, it's 2+. It looks like a 3, but it's not. Okay, so this is the way you would do it anyway. So the anode is over here. Oxidation occurs here, and the cathode is over here. Reduction occurs here. All right, so that's it. Next slide. And here we have what we just drew. The only thing is that you could also put in the concentrations, and I think that might be the way that it's done typically, but you won't always see that. Next slide. All right, this one's a little hairy. It's not difficult. So what we'll need to do, so let me just read it. ClO2, which is produced by this reaction, blah, 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 has been tested as a disinfectant. Using the data from the table, which we're going to go to in a moment, find E0. Okay, that's the standard cell voltage. So we'll just read that right out of the chart, just as we've been doing. And then to get the delta G standard, we use that formula, which is, if you'll recall from the lecture notes, it's delta G, and in this case it would be delta G standard equals minus NF E standard, where the N is the number of moles and the F is Faraday's constant, 96,485, and that's the number of coulombs in a mole. So what we'll do here is we'll have to figure out what is N, so let me just write that. N equals something, and so let's just look over here and see if we can find out what N would be. How many moles of electrons would be transferred for every one of these reactions? And your clue here, if you see something like Cl2 and you've got just Cl somewhere else with a 2 over here, it's a good indication that you're going to have 2 electron moles transferred. So let's just write that. N equals 2. This one is not that hard. And really most of the time they won't be. They'll usually either be 1, 2, or 3. In this case we're going to go with 2, so N is 2. F we already know, so NFE, so we just have to figure out what the standard cell voltage here is. And then we should be good to go to be able to do the rest of this problem. Now, before we move over, one of these things, either the Cl2 here or this ClO2, and notice what I've written here on the left-hand side, ClO2 minus is what that actually is. So it's this thing right here on the left is Na plus ClO2 minus, and over here it's just ClO2. So what that means is that there's an extra electron over here on this side, which I've got also pointed out right here with this minus charge. So ClO2 minus. So if the way it's written here, ClO2 minus is going to ClO2 0, which means it's losing an electron, which means it's being oxidized. So I mean, if you want, we can just go ahead and write that. So O here for this species, and then this Cl2 here is going from 0 to -1, and we can see that because NaCl is Na plus plus Cl minus, right? So it's gaining an electron, so it's being reduced. So this thing right here is being reduced. So that's the reduction half reaction. Let's go to the next slide and figure out the standard cell voltage and look at this some more. So here at the top, we see the Cl minus thing, Cl2 going to Cl minus, which is the way that this is actually written in that reaction right here. The ClO2 minus and the ClO2 are in the reverse direction here as they are on the previous slide, which means that we have to reverse this. We have to put the ClO2 minus over here and then the ClO2 neutral over here, and then that means that we have to change this from plus to minus. So to get the standard cell voltage, we add 1.36 plus 1.36 minus minus 0.954. So that's going to be approximately 0.4, not exactly, but about. So the standard cell voltage here is going to be about 0.4 volts. Let's go to the next slide. And we can see here what it actually is. It's 0.406. 0.406. Okay, so anyway, that's the first part. Find E naught or E standard, and then to get the delta G, we use delta G equals minus NFE, where N is going to be 2 here, and F, of course, we know that's just a constant, Faraday's constant, 96,485, and that's coulombs per mole of electrons. And then when we multiply that by 2 moles of electrons, that will convert the units to coulombs. And then when we multiply times joules per coulombs, we get joules, which we want joules for the energies, and free energy is a kind of energy, right? So we want this to be in joules. So anyway, when you multiply this out over here and do the math, you get minus 78,346 joules, or you can write it as minus 78.4 kilojoules. All right, so we've done everything we were asked to do. Let's go ahead and move to the next problem. Consider only these species at standard conditions: Na plus Cl minus, Ag plus Ag, zinc 2 plus zinc, and lead. I'm terribly sorry. The room that I have to do this recording in is just full of allergens. So we're using only these things that I just underlined, and I did a bad job of it. Which is the strongest? So A is which is the strongest oxidizing agent. So the way that I recommend that you read that is which one is the most likely to be reduced. So I'll just write R here. And then which is the strongest reducing agent. To make it less difficult to understand, I recommend that you just rewrite that as which is the most likely to be oxidized. In other words, which is the most likely to give up electrons. And for part A, it's which one is the most likely to gain electrons. And remember that the table that we're given, the standard reduction potential, is written such that we're writing all the half reactions with being gained, with electrons being gained. Okay, so this one's a little tricky until you figure out how to do it. So what I did was I transposed all of these things here at the top over to the next slide at the top of the chart to make it easier for us to see what's going on. So why don't we go ahead. So remember that the first part, A, we're trying to find the thing that's most likely to be reduced. And we have to choose just from these things right here, not from what they go to or come from in the chart, just what is written there. And then for part B, what's the thing that's most likely to be oxidized? All right, so before we switch, the thing that is most likely to be reduced, in other words, the answer to part A, is going to be in the chart from top to bottom the way it's written, because the chart is written as things are being reduced. So in other words, from the top to the bottom, the things at the top are more likely to be reduced, and that's why their number is more positive. Let's go to the next slide. Excuse me. So up at the top here, I've written the things from the problem statement. So we only want to look at those things, not the things that they transform into or from. So I've got everything here circled in red. A couple of these things like the silver here and also over here the zinc, we're actually looking at both things. So we're looking at the thing on the left and on the right for those two. The other ones we're just looking at one. And so for the first part, A, we're looking for the thing that's most likely to be reduced. It actually said would be the best oxidizing agent, but that's the same thing as being reduced. And so because this is a standard reduction potential chart, then it's actually written in that direction. It just is all written such that everything is being reduced. And if you get a problem like on the final or on another exam where they just give you a list of 2 or 3 of these things, then the way that you check it to see if it's the same format as this chart would be just to look to see if the thing on the left-hand side of the arrow is gaining 2 electrons, which you can see, or 1 electron, which you can see. Everything in this chart is gaining an electron on the left-hand side of the arrow and then making it into something else. So the things that are what we would have called most active in 1311 when we did the activity series are down here on the bottom, and they are written on the right-hand side. So first of all, Cl minus is the first thing we see here in our list, but it is on the incorrect side. It isn't on the left, it's on the right here. So that means that it won't work for this particular part of the problem. So we go to next, silver. In fact, actually the easiest way to do this problem is just to look at everything on the left and then find it and see if it matches up with something here in this list at the top here. So Cl2 is not on that list, right? If you look back up here at the top, you don't see Cl2. You see Cl minus, but Cl minus is over here on the right-hand side, and we don't want that. We only want the things on the left for part A. And then for part B, we'll switch. So now we come down, and the next thing we see is Ag plus. And I'm only doing the ones that I have in the red boxes, and the way I did the red boxes was just by choosing everything in that list at the top and then circling it. So silver plus is in that list, and it is at the top. It has a voltage to be reduced to 0.8, and it's plus 0.8 volts. So what that means is that this is going to be our answer right here for part A. So I'll put a star, and then I'll write A here, and that's telling us that that's the one that's most likely to be reduced. Or to say it another way, the best oxidizing agent. All right, so what do you think we're going to have to do for part B? We want the best reducing agent or the thing that's most likely to be oxidized. So these are not written in that direction. None of them are. To be oxidized, we'd have to start with something like this lithium at the bottom and then draw the arrow in the other. We'd have to switch it so that it's lithium, metal, arrow, lithium plus electron. And of course that would reverse the voltage. In other words, what we want to do is now, for part B, we want to look at the things on the right-hand side of the arrows. And also, all of these voltages here would then be reversed. So, for example, this one would become plus if we reverse it. So actually now this would become the top, and then this thing up here with the F2 would become the bottom. So what we want to do is we want to start here with sodium, and that would actually be the answer if it were in the choices here. But it isn't. We have Na+, but that's on the wrong side again. So now we're looking for things on the right side. So let's move up now to our next possibility, which is going to be zinc. And is that one in the list? Yes, it is. It's right there. So there's our answer. So the thing that's most likely to be oxidized is going to be this one right here. So the answer to part B is going to be zinc. Next slide. And so here are your answers. If you didn't catch that, if you want to pause this and read over this, this will go through it again. All right, so next slide. All right, galvanic cell is based on the following half reactions at 25 degrees centigrade. And I wrote the little voltages over to the right-hand side. So Ag plus E minus gives Ag, and it's 0.8 volts. So we can try to picture in our minds where these are going to be located in the chart. And then H2O2 plus 2H plus giving 2H2O is 1.78 volt. And I'm trying to do this so I don't accidentally go up and obliterate the numbers. So which of those two numbers is larger? Which one would be above the other one? The H2O2 plus 2H plus is going to be on top if it were written in the chart. So they've got them backwards. They've got them upside down. So the thing on the top would be the H2O2 plus 2H plus 2 electrons gives 2H2O. So if you were looking at these in that standard reduction table, this would be on the top, and then the silver one would be on the bottom. And so we leave the one that would have been on the top, this one, alone, and let it stay the way it's written, and that would be plus 1.78 volts, and then we reverse this one on the top so that we would write it where the Ag would be over here, the metal, and then the Ag plus would be over here, and so we would also have to reverse the voltage here. So this would become minus, and when we add these together, it's about 1.8 volt minus 0.8 volt, so it would be about 1 volt. It wouldn't be exactly that, but about that. So about 1 volt would be the standard cell voltage. Actually, they didn't ask us to figure that out, but it won't hurt that we did it. All right, so predict whether each cell is larger or smaller than the standard cell voltage. And there I did it again. It's so hard to do this. So the difference here is that the standard cell voltage here would be about 1 volt, and that, so this one would be about 1 volt, and that never changes. The cell voltage, however, can change. It can be larger than 1 volt, or it can be smaller. It can go all the way down to 0. So the E without the degree sign is the one that it actually is at this moment. So for example, if you've got a 5 volt battery and you've run it halfway down, you're at 2.5 volts. If you keep running it long enough, it'll go to 0. Okay, so we're supposed to see if the cell voltage is larger or smaller than the original voltage. So what we need to do is we need to realize that if we leave this one written the way it is, this one right here, then the reactants are going to be H2O2 plus H plus. And if we reverse this one at the top, then this Ag plus here is going to become the product. And notice here, over on the right-hand side, I wrote arrows to show whether they're going to be going in the direction written or if they're going to have to be reversed. So the product here is going to be Ag plus. So that's going to go on the right. So there's two different ways we can do this. If we use this equation right here and just kind of get an idea, we don't actually have to do the whole problem, but we can just figure out what the mathematical situation is going to be. So for A, notice that the product, Ag plus is the product, is still 1 molar. So that's the same as it would have been for the standard cell voltage, but the reactants have increased. Both of them are now 2 molar. So whenever you have an increase in the concentration of the reactants, it will, if you'll remember from chapter 15, it drives the equilibrium to the right, which means that the voltage will get larger. Another way you could look at that would be to go ahead and do your Q value. Q is reactants under the products over reactants. So in this case for A, it would be 1 over 2. So Q would be 1/2. Let me just point to it. So we're down here in this little equation, the Nernst equation. Q would be 1/2, and the log of 1/2 is minus 0.3. And the only reason I know that is because, and I can't do these in my head, but I've just done this one so many times. It's minus 0.3. So, and N here is going to be 1 because silver is plus 1. So we're going to end up with whatever the original voltage was, which was about 1. So this was originally going to be about 1. N is 1, so we're going to wind up with 0.3 times 0.0591. So we're just multiplying this, and they're both negative. So this is negative, and this is negative, so that's going to become plus for part A. And it's going to be about 0.0 I think it's actually a little bit more than 1. So 0.01. Okay, and then that would be added, anyway, whatever the original voltage was, it would be added to that. So 1 volt, which it was originally, which is the E naught, plus 0. Anyway, you can do it either way you want. That's actually a little more complicated, and we aren't really required to do it that way, the way I just did it, because the problem statement is just asking us which one is, whether it's going to be larger or smaller. So that's kind of like overkill. But either way you do it, you see that for part A it's going to get larger, so I'll just write L here by A to show you that it's going to get bigger. And then for part B, the product has increased and the reactants have either stayed the same or gotten smaller. So that's an indication that we're running the cell down. So, I mean, just common sense is going to tell us that the voltage is smaller than the original voltage when you started off at 1 molar concentrations. So you could also put 2 over 1 and just forget about the one on the right, which means you're going to be taking the log of 2, which I think that's actually plus 0.3. So plus 0.3 times 0.059 is going to be like 0.01. So you would be subtracting that, though, because you don't have this second negative. Now it's over here. This is going to become plus 0.3, I think, but it's going to be plus anyway, whatever the number is. And so when you multiply a plus times the minus here, this one, you get a minus. So you're subtracting away from the original voltage. So it will be smaller. Or it would be easier just to look at it and say, okay, we have more products than we had originally, so we've increased the products concentration, and according to chapter 15, according to Le Chatelier's principle, if we increase the concentration of the products, it drives the equilibrium to the left, which in this case means that the actual voltage of the cell will be smaller. So for part B, we'll put S to show that it's smaller. Okay, so there's several more slides here. If you want to stop and pause them and look at them, you can. Otherwise, I'm just going to go on through because we've already talked about all of them. So let's go to the next slide. And here are the voltages. We're going to wind up having 1.78 here minus 0.8, which is going to be a little bit less than 1. Next slide. Here, this slide gives you the balanced equation. Next slide. And here are the answers. So for part A, as we said, it's going to get larger. The voltage is going to get larger. And for part B, it'll get smaller. So a rule of thumb here, if you want to try to remember it this way, is that if you increase the reactant concentration, in other words, if you started out at 1 molar for your reactants and increase them, like here for this one, for part A, it's 2, then you will drive the equilibrium to the right according to Le Chatelier's principle, and that means the voltage will increase. So you would actually be increasing your voltage. For part B, whenever you increase the concentration of the products, which is what's happening here in part B, Ag plus is the product, then you're going to drive the equilibrium back to the left, which means that the voltage of the cell will be smaller. And part B is what actually happens when you run a battery like on your cell phone or whatever, and if you keep running it, then it will reduce the voltage that's available until it gets to 0. Next slide. Okay, this is a concentration cell, so we have to remember that there are a couple of rules that apply here only to concentration cells, okay, and those two rules are as follows. First of all, whenever you have a concentration cell, you want to write the smaller concentration on the left of your diagram. We're going to see here when we get to part C that we can't do that because notice here they've got one diagram and we have to use it for all three parts. So that means that for part C, it's going to be going in the wrong direction, but it's not a big deal. But basically for a concentration cell, I recommend you put the lower concentration on the left so that your electron flow will be from left to right because that's the way we've been doing it. The other rule is that whenever you figure out your Q value here, you're going to put the smaller concentration on top. And if you can just remember, put the smaller concentration on top, it will save you a lot of time. So we're going to do part A, B, and C, and I'll look very briefly at E. We're going to skip D. So consider the concentration cell shown below. So down here we have a concentration cell, and it's a concentration cell because we have the same thing on both sides. We've got silver on both sides. So it can still generate a little bit of a voltage if you vary the concentrations. The standard cell voltage for any concentration cell, this right here, will be 0 every time because there's no potential difference between silver and silver or whatever. There's no potential difference between gold and gold or any other metal, copper and copper, so it's always 0. So this first part will always be 0. And then Q is going to be product concentration divided by reactant concentration. All right, so for part A, we're going to put 1 here, and I'm going to write it at the top. 1, and it's 1 over here on the left-hand side also. So what would Q be? Q would be products over reactants. It's going to be 1 over 1, which is 1. And so log of Q would be log of 1, and the log of 1 is what? 0. So this whole term, this whole part here just kind of vanishes. And we're just left with E equals E naught. But E naught is 0. So that means that the voltage is going to be 0. So for part A, it's just going to be 0. And it will also, I'm not really doing part E of this problem, but just glance at it for a minute. What would the potential be if both sides are 0.1 molar? It would be the same answer. Q would be 0.1 over 0.1, which means the log of Q would be 0. 0 times everything else in that term is 0. 0 minus 0 is 0, so the voltage is 0. So if we did E, we would also get 0. So I'll just write that in. All right, let's go to B. The one on the right now is going to be 2. So let's write 2. Okay, so we want, and notice that this is still the same way we've been doing it, so that we have the smaller concentration on the left, which is what we want, so the electron flow is from left to right. And we want products over reactants, but for concentration cells, we want the lower concentration over the larger. And the lower one is going to be 1, and the larger is going to be 2. So that means that Q is going to be 1/2. And the log of 1/2 is 0.3. Just very briefly, 0.3. That would be the log of 1/2. And then we would multiply that by 0.0591 divided by N, but N here is going to be 1 because Ag is a oxidation state of 1 always. So you can forget about the N for this problem, so it's just going to be 0.3 times 0.0591. And that's going to end up being about 0.01 if memory serves. So we're going to be subtracting that from E naught, which is 0. Okay, so whatever we've got there, we'll go ahead and flip over to that in just a minute. But for part B, basically we're going to end up here with negative 0.01 approximately. So let me just write that in here. And I'm going to change it to plus because this log of 1/2 is actually negative 0.3. So my mistake. So when we multiply the negative times the negative here, we get a plus. So instead of being negative 0.01, it would actually be plus 0.01 volts for part B. And then for part C, now this one is going to be different because we've got 0.1 here on the right hand side, and this is going against our convention because we've got the lower concentration on the right. So we're going to have the electron flow will be from right to left for this particular problem. When we do the Q value, we want to put the lower number on top. So I'm going to come up here in an empty spot and write this. So we have the smaller or lower number on top and the larger number on the bottom. So 0.1 here is going to go on the top, and the other one, the 1 here, is going to go on the bottom. So what is 0.1 divided by 1? It's just 0.1, which we can rewrite as 10 to the minus 1. The log of 10 to the minus 1 is just the exponent of that, which is minus 1. So that means that this part right here is going to be minus 1. Minus 1 times minus 1 will be plus, and then it will be multiplied by 0.0591. So it's going to be plus 0.0591 for this part right here. I'm just going to write this as 0.059 to save some effort here. Okay. Okay, let's go to the next slide. So for part A, we're going to end up just with 0, as we said, because we don't have any difference in concentrations, and we also don't have any difference between the two metals. For part B, we wind up with plus 0.018 actually. So that's about what we said. And then for part C, next slide, we end up with plus 0.0591. So you can pause these slides and look at the answers at your leisure. Let's go to the next slide. Number 7, I'd like for you to do on your own. It's very simple. We have a zinc copper cell, so you're very familiar with that. So just figure out what the voltage would be after we let this thing run for a while. So, I mean, that should give you a hint as to whether it should be getting larger or smaller. Remember, the basic cell voltage here is 1.1 volts. So we're going to let it run until the concentration of the zinc has changed by 0.2 moles per liter. So I'll let you figure out whether it's going to get larger or smaller. So we need to look to see whether the zinc 2 plus is a reactant or a product. Next slide. Okay, electrolysis. What mass of each of the following substances can be produced in 1 hour with a current of 15 amps? So we want to multiply 15 amps, which is 15 coulombs per second, times the number of seconds. In this case, it's 1 hour. 1 hour is 60 minutes, and each minute is 60 seconds. So 60 times 60 would be 3,600 seconds. Multiply that times 15. And whatever you get for that, then you want to do two more things. First of all, you want to divide by F and then divide by N. What is N going to be? Well, we're going from cobalt 2 plus to cobalt 0, so we're going to figure that N is probably going to be 2. And then Faraday's constant is just 96485, and that again is the coulombs per mole of electrons. And once we've done that, we will have the number of moles of cobalt, and then we just multiply that by whatever the molar mass for cobalt is. Next slide. So multiply 15 amps times 3,600 seconds, and then divide that by 96,485, and then divide that by 2, which is coming from this, and that's going to give you the number of moles of cobalt, and then just multiply that by the molar mass of cobalt, which down here is about 59 grams per mole. So again, multiply 15, this was in the problem statement, and then 3,600 is the number of seconds in 1 hour, and then whatever we get here, which is 54,000, divide it by F, the Faraday constant, and then divide it by 2, which is coming again from this right here, and then that gives us the number of moles of the cobalt metal, but they're asking for the mass, so back up in the problem statement here, they want the mass, so we have to multiply by the gram atomic mass, which is about 59 grams per mole, and so that gives us about 16.5 grams, which I've rounded to 17 because of sig figs. So these electrolysis problems are usually pretty easy. Next slide. Okay, let's go to the questions from Mr. Mack's website. Next slide. So number 9, they give us a table of half reaction potentials. This is taken right out of the table of standard reduction potentials. And we can tell that because we're seeing here that everything is written such that everything is gaining electrons. So we're going, for example, F2 plus 2 electrons and so forth. So this is the table of standard reduction potentials, and it's really what we want, right, because it's what we're used to. So anyway, the question down here is asking which of the halogens in this table is the strongest oxidizing agent, which we're going to read that as being which one is the most likely to be reduced, and that just means it's going to be the one at the top of this chart unless they switch the order up, which they didn't. So just check it real quick. All of these numbers are getting smaller and smaller as you come down. So that means we just read up to the top, and if that's one of the answer choices, which it is, that's going to be the answer is F2. So that answer choice D is going to be the one that's correct. Next slide. And so answer D, next slide. Which one of the following types of elements is most likely to be a good oxidizing agent? So let's reread that the way it's easier. Which one of the following types of elements is most likely to be reduced? So let me just write that up here. Which one is most likely to be reduced? Again, it's so hard to write with this thing. So what do you think? Most likely to be reduced. Wow. I went through all that trouble and then you still can't read it, but anyway. In other words, which one is the most likely to gain electrons? So looking at this, these are all arranged so that, well, except for transition elements, basically, and lanthanides, but B, D, and E are all columns or groups in the chart, and B and D are things that don't want to be reduced, right? They want to actually be oxidized. They want to give up electrons. So which ones want another electrons? Well, the answer is E. Things that are in the 7th column want to be reduced because they want to go from 7 electrons to 8 electrons in their valence shell, so they'll have a complete octet. Next slide. So here's your answer, E, halogens. Next slide. Number 11, they give us another table. This one is not in the right order. So first of all, this number 19 at the bottom says the standard cell potential of the voltaic cell based on this reaction below is blank volts. So when they give you a problem where they say based on this reaction, you have to do it the way they have it written, even if it winds up being negative. Now, if it winds up being negative, it means it won't run, but you still have to leave it that way. So notice here we're going from SN2 plus to SN4 plus. So let's check the chart. SN2 plus going to SN4 plus. Well, we want it to go the reverse direction the way that one is written. So we can do that. We can reverse this thing and go this way. So we'll just reverse these, but that means that we also have to change the sign in front of the 0.15. So that becomes minus 0.15. And then going from Fe3 plus to Fe2 plus, that's going to be this one right here. So that one is going in the right direction, the correct direction, so we leave it alone. So to get the voltage for the cell, we would add plus 0.771 volts to minus 0.154 volts, and that's going to be about 0.62 volts, which is the closest answer here. And I'm sure this is what you would actually get if you did the addition on a calculator, is C. Now, before we move any further, notice here that when we multiply that by 2, and we multiply that by 2, it doesn't change the voltage, because voltage is an intrinsic property of the metal, and it doesn't depend on how much you have. Okay, number 20. The standard cell potential of this cell below is blank volts. So here, SN4 is going to, 4 plus is going to SN2 plus. So that's the same one that we had here before, but this time it's going to go in the direction it's written. So we're going to have plus 0.15 volts for that one, and then we have chromium going to chromium 3. So that's this top one here, but it's going to be going in the opposite of the way it's written. So it's going to be going in the reverse direction. So we reverse this half reaction and change the minus to plus. So that becomes plus 0.74 plus 0.15 is about plus 0.89. And that's going to be answer choice A. So we've got answers of C and A. Next slide. Next slide. All right, the relationship between the change in the Gibbs free energy and the E of a cell is given by, and I'm just going to go ahead and tell you the answer to this one. It's very straightforward. It's going to be E delta G equals minus NFE. Next slide. Next slide. We get another little list of half reactions. Which of the following reactions will occur spontaneously as written? So what you could do as an exercise is just to go through all 5 of these and convince yourself that 4 of these are going to wind up as negative numbers, which I'm not going to actually do that, but I'm going to call your attention to B, because we actually just did this a couple of slides back. We went from in fact, I think it was the same exact equation. We went from SN4 to SN2, and we went from chromium to chromium 3 plus. So it would have involved this one right here and this one right here, and the one on the top would be reversed, and we got a voltage of 0.89. So the B one is going to go forward the way it's written, because you get a positive value when you add those two things up. Again, you're going to be adding plus 0.74 to plus 0.15, and the voltage winds up being plus 0.89. If you do the other 4 as an exercise, that would be this one and then these 3 down here, you should get a negative number, and you will get a negative number. So that means that they will not run spontaneously. You could make them run, but you'd have to put a current through them. Next slide. So the answer is B. Next slide. Okay, 14, the standard cell potential E naught of the cell for the reaction below is 0.63 volts. The cell potential would be blank if we change the Pb concentration to 2 times 10 to the minus 4 here. Okay, so we need to look at our reaction, and they were nice enough to provide us with that. So we have Pb2 plus is the reactant, and zinc 2 plus is the product. It's products over reactants. So let's write that out. Products over reactants. P over R, that's going to give us our Q, which I'm not going to write that because it takes too long. So what will that equal? Okay, so let's look at it. So what's the product? So find it. Product is what? Is it zinc 2 plus or Pb 2 plus? And we don't worry about the zinc or the Pb because they're solids and they have an activity of 1. So forget those. So which one is the product? It's going to be the zinc. And what concentration does the zinc have? 1 molar. So put 1 over whatever the concentration is of the reactant, which in this case the reactant is the lead 2 plus, and its concentration is 2 times 10 to the minus 4th. So this is going to be 2 times 10 to the minus fourth. And that's what our Q is going to be. So this is Q. So let me just write it over here. Okay, so 1 over 2 times 10 to the minus fourth. Let me just teach you a little bit how to figure these out in your head, kind of. That's going to be 1/2. We could rewrite this as 1 times 10 to the minus 0, right? Because 10 to the minus 0 is just 1. So let me do that. And then what you can do is you can just do the numbers first. Well, you're going to get a half, or let's write it as 0.5, and I'm going to leave off the 0 for time's sake. So just write it as 0.5. That's just 1 divided by 2. That's the number part over here, this part over here. And then do the e part next. So e to the 0 minus e to the minus 4. That's 0 minus a minus 4 is plus 4. So it's going to be 0.5 times 10 to the plus 4. Which you can rewrite as 5 times 10 to the third, which you can rewrite as just 5,000. So that is going to be Q. To get log of Q, can I just write this as 5K? Because number one, it'll save time, and also I'm out of room here. So 5,000 is going to be Q. So that's Q. What would log of 5,000 be? Well, it's, okay, so 10 to the first is 10, 10 to the second is 100, 10 to the third is 1,000. We want 5,000, so 10 to the fourth is 10,000. So it's about halfway between 1,000, which would be 10 to the third, which would have a log of 3, and 10 to the fourth, which would be 10,000. It actually isn't about halfway through because the logs don't go that way. But just to make this a rough estimate, let's just write it as 3.5. Okay, so that would be approximately the value of a log Q. What is that multiplied by? Well, here, what is n going to be? It's going to be 2, because both of these are 2 plus. Both need 2 electrons, 2 moles of electrons to get them to the metal. So n is going to be 2. Let me write that at the top. So n is going to be 2. And then the other thing we need is the 0.0591. So what we're going to wind up with is going to be 0.05. I'm not going to even try to write all this out. What we're going to wind up with here is 0.0591 divided by 2, and it's all done on a slide after this. And then that's going to be multiplied by something like maybe 3.4 or something like that. And then we're going to subtract that. That's going to be a positive value. We're going to subtract that from whatever the standard cell voltage is, and that is going to be plus 0.63 volts. And the reason we know that is because they gave it to us. However, we could also look it up in the chart, right? So if they didn't give it to us, we'd just go to the chart and look it up. But it's 0.63 volts, so it's E standard, which is 0.63 volts, minus 0.0591 divided by n times log Q. Log Q is 3.5 and n is 2. So let's just say, just to get a ballpark idea of what your answer should be, if you just divide the 3.5 by the 2 first, that's a little bit less than 2. And then when you multiply that by 0.0591, you get maybe about 0.1. Now, this is just a rough estimate, but it's a good way to do it because it gives you an idea if your answer's right. So you would wind up with your voltage, the actual voltage of the cell, or actually let's write it as E because that's the way they usually do it in this book, would be, 0.63, which I'm just going to write this as 0.63 volts. That's the E standard, minus that other term which we decided was about 0.1. So what is 0.63 minus 0.1? It's about 0.53. Okay, so let's go ahead now and move on to the next slide and see if we got this right. I think it's going to actually wind up being 0.52, but let's go to the next slide. Okay, so down here at the bottom, answer, use the Nernst equation. Zinc is going to be the product and lead is going to be the reactant. So just as we said, 0.63 is going to be the standard voltage, which was given to us in the problem statement here, and then minus 0.0592. I've got 2 here, and I think I've got it written as 1 in other places, because I think it depends on the source you use, and really, to be honest with you, it doesn't matter. Divided by 2, that's our N, and then divided by the log of the products over the reactants. So the products is 1, the reactant is 2 times 10 to the minus 4th. This is in the problem statement. Just what we did. We were estimating it at about 3.5, and it actually turned out to be 3.7 approximately. But I mean, we got a ballpark figure, right? And we said the answer should be 0.63 minus whatever we get when we do the math for this part right here, which we said would be about 0.1. And it turned out to be 0.11. So the actual answer when you do this in your calculator is 0.52 volts. Okay, so I mean, obviously when you're doing a test, you want to go ahead and just do it on your calculator. So what I'm doing when I'm doing this in my head is just a way that I can do it where I can kind of tell you how to do the problem where I don't have to keep flipping slides to the answers, because when I flip to the answer, it kind of takes away the suspense. Next slide. Consider an electrochemical cell, number 15, based on the reaction 2H plus SN gives SN2 plus H2. Which of the following would change the cell potential? All right, so anything that changes the concentration of either the reactants or the products here will be something that will change the potential. So here, this is a gas. So this actually comes into play here. Whenever we have a solid, a pure solid or a pure liquid, we leave it out. So we leave this one out of the equilibrium, but the gases are not in that same category. So let's go through these A through E. A, lowering the pH, what would that do? It would lower the H plus concentration, which means it would change the concentration of a reactant, so that would change the potential. So again, anytime we change concentration of reactant or product, it will change the potential because it's changing the equilibrium. B, increasing the pressure of H2 gas will change the pressure of a product, or, I mean, it will also increase the amount of it. So that means it will drive the equilibrium to the left. C, increasing the SN2 plus, that will also drive it to the left. D, increasing the pH means we're increasing the H plus, that will drive it to the right. So the answer is going to be E, any of the above will change the measured cell potential. Next slide. Next slide. One of the differences between a voltaic or galvanic cell and an electrolytic cell, remember the electrolytic cell means like you're recharging a battery, or alternatively it means you're plating something out like a metal. What is the difference? The electrolytic cell is causing a non-spontaneous reaction to occur. And it's doing that, I'm sorry I just erased half that, but it's doing that by forcing a current at a higher voltage than the cell would originally have produced in the wrong direction. And so you have to keep it, like if you have a cell phone that runs on, let's just say, I don't know what mine is exactly, but let's just say it's 5 volts. Then in order to recharge it, you'd probably want to run it at about maybe let's say 5.3 volts, just to make sure that you're not going to have anything coming back in the reverse direction. Otherwise, it'll just, as you try to recharge it, it'll just keep discharging. So you want to have it a little bit above the original voltage. In a car battery, I actually have a gauge that shows me that when it's charging, I mean, assuming that the gauge is accurate, it isn't actually trying to charge at 12 volts, it's charging at about 13. So it's a little bit higher than the original voltage. The point here, and this is kind of important, is that you're forcing something to happen that wouldn't happen ordinarily. Okay, look at A. This one's the one that confuses a lot of people. Electrons flow towards the anode. Well, that would be true if you still had the same setup you had before. In other words, if you still had electrons coming out of the, let's just say the anode's on the left originally, like it usually is, then that means that you would be causing the electrons to flow back to the left-hand side, but that's no longer the anode. The anode is where the electrons originate. So when you force a non-spontaneous reaction to occur, you're forcing what was originally the cathode to become the anode. C, an electric current is produced by a chemical reaction, is what would happen for a voltaic cell, but that's not the difference between an electrolytic cell and a voltaic cell. O2 gas is produced. Choice D is completely irrelevant. It's a nonsense answer. And E, oxidation occurs at the cathode. The definition of the cathode is that the cathode is where reduction occurs. So our answer choice here is going to be B. Next slide. Next slide. How many grams of calcium metal can be produced? Calcium's 40 grams per mole. The electrolysis of molten calcium bromide, so that's telling us that N equals what? If it's CaBr2, Br is what? Br is -1, right? Because it's in the 7th column. But we have 2 of them, so that's -2. So calcium has to be what to match? +2. So N is going to be what? 2. All right, so we're going to divide at some point by 2, and we're going to have 30 amps. That's 30 coulombs per second. It's that by definition. So 30 coulombs per second times the number of seconds. So 1 hour is 3,600 seconds, as we said before. So 10 times 3,600 is 36,000 times 30 coulombs per second. So whatever you get when you multiply 30 times 36,000 will give you the number of coulombs. And I can't really, I mean, I could do that in my head, but I don't want to. So we'll get to that in just a minute. Whatever you get there, you're going to divide that then by F, the Faraday constant, 96.485 coulombs per mole, because we want to get this transferred over from coulombs to moles of electrons. But we still don't want to stop there because we don't want the moles of electrons. We want the number of moles of electrons it would take to convert Ca2 plus to Ca, and that would be 2. So we still have to divide that last term by 2 to get the number of moles of calcium. And then since they asked us for the mass or grams, we then have to multiply that by the gram atomic mass of 40. Next slide. So, I mean, hopefully by the time you do this one, you'll start to catch on. These are really easy. So just the amps times the time in seconds divided by 96.485 divided by N, and that will give you the number of moles of whatever metal you're dealing with, and then multiply that by the gram atomic mass. So when we do all of this and we multiply by 40, we get 224 grams of calcium. So there's our answer. Oh, and that is answer choice D. Next slide. And we have more things here that are available if you want to go check them out. I don't recommend you really do that unless you have time at the end, but if you do have time, it can be especially beneficial if you can go through and just kind of, I mean, you don't have to do all of them. If you see one that's just, you know, way out of left field, then just skip it and go on to the next one, but it's some good practice. Okay, next slide. All right, so that wraps up the work problems for Chapter 20, and it also wraps up Chapter 20. So next we'll be going to nuclear chemistry, Chapter 21. This is kind of like the end of the basic course in 1412, the way it was traditionally taught. Now they're also adding in a little bit on nuclear and organic chemistry. So those are just survey chapters, which we'll go through kind of quickly. But basically, this wraps up our course. We'll still go ahead and do 21 and 24, but they don't take as much time as the ones that we've done up to this point. So I'll see you in the lecture notes for Chapter 21.